These are notes for AP Calculus on the topic of increasing and decreasing rates in real-world applications. So let's first draw the picture of what each of these look like, and then we'll look at what's happening with the first derivative and the second derivative. So if something's increasing at a constant rate, that'd be a linear equation like that. And since it's increased, that means the first derivative, f prime of x, would be positive, greater than 0. And the second derivative, since it's not concave up or concave down, it wouldn't be positive or negative. The second derivative would equal 0. Similarly, if something's decreasing at a constant rate, that means the slope or rate is constant. That'd be a linear equation with a negative slope like that. So that means since it's decreasing, the first derivative would be negative or less than 0, and the second derivative, again, since it's not concave up or concave down, would equal 0. Now let's look at the cases where it's not just linear, it's not a constant rate, if the rate itself is changing. So increasing at an increasing rate. Well, increase from left to right at an increasing rate, would be something like that. First derivative would be greater than 0. And since it's concave up, since the slope itself is increasing, the second derivative would also be greater than 0. Decreasing at an increasing rate would be like that. Decreasing, so the first derivative is less than 0. The rate itself is increasing because the slope is getting less negative as we go along. So it's actually increasing. And notice it's still concave up. So the second derivative is greater than 0. It's concave up. So if the rate's increasing, you can see the graph is concave up. The second derivative is greater than 0. Now let's look at the other two cases. Increasing at a decreasing rate would look something like that. The first derivative here is greater than 0. It is positive. It is increasing. But the second derivative is less than 0, since it's concave down. You can see the slope itself, or rate, is decreasing. And finally, decreasing at a decreasing rate, like that. So it's decreasing, so the first derivative is less than 0, and it's concave down, or the rate itself is decreasing, getting more and more negative, so the second derivative is less than 0. So now let's take a look at, we have a table of values. It says let f be a differentiable function, just means you can find the derivative everywhere. That's strictly monotonic. Remember, strictly monotonic means always increasing or always decreasing, one or the other. So in other words, the first derivative is not going to change sign. It'll either be all positive or all negative. And no inflection points. Well, if there's no inflection points are where the graph changes concavity. So this basically tells you f double prime of x does not change sign. So it says determine the sign, in other words, whether it's positive or negative, of f prime of x and f double prime of x for the given table. Then state whether f is increasing at an increasing rate, decreasing at a decreasing rate, decreasing at an increasing rate, or decreasing at a decreasing rate. So we just have a few points on the graph, basically. Here's the x-coordinate, here's the y-coordinate. So the best we can do to figure out what's happening with the rate or the slope is to look at these points. So let's first see if this function is increasing or decreasing. You can see the y-values go from 7, 10, 12, 13 as x increases. So since those are increasing, we know f prime of x is greater than 0. So we know it's increasing. To see if the rate or slope is increasing, you got to look at the change in the x-coordinate and the change in the y-coordinate. Here, the change in the x-coordinate keeps increasing. Between 3 and 4, it increases by 1. Between 4 and 5, 1. 5 and 6, 1. Now let's look at the change in the y-coordinate, which f of x represents. From 7 to 10, it increases by 3. 10 to 12 increases by 2. 12 to 13 increases by 1. And then to estimate what's happening with the slope, or rate, the derivative is the slope at a single point. The best we can do here is to estimate the derivative or slope between these points by looking at the change in the y over the change in the x. This would be 3 over 1, 2 over 1, and 1 over 1. So that would just be 3, 2, and 1. So you can see the slopes, 3, 2, 1, those are actually decreasing. So that means double prime of x is less than 0. So this one would be increasing at a decreasing rate. Let's take a look at another table. Here again, let's look at the y values, 3, 6, 11, 16, those are increasing. So we can see f prime of x would be greater than 0. And again, let's look at the change in the x-coordinate, delta x, and the change in the y-coordinate, delta y. The x-coordinate from 5 to 7 increases by 2, 7 to 10 increases by 3, 10 to 12 increases by 2. The change in the y-coordinate from 3 to 6, it increases by 3, from 6 to 11 increases by 5, 11 to 16 increases by 5. So again, let's look at the change in the y over the change in the x. So it'd be 3 over 2, 5 over 3, and 5 over 2. So if we put these as a mixed number, that's 1 1/2, 1 2/3, and 2 1/2. So you can see 1 1/2, 1 2/3, 2 1/2. Those slopes are actually increasing. So since the slopes are increasing, that must mean that f double prime of x is greater than 0. So this is an example of a function that's increasing at an increasing rate. F is increasing at an increasing rate. Take a look at another. This time, 14, 9, 5, 3. You can see the y values are actually decreasing. So f prime of x is less than 0. And again, if we look at the change in the x-coordinate and the change in the y-coordinate, 6 to 8 goes up to 2, then by 2, and by 2. The y-coordinate 14 to 9 goes down by 5, so negative 5, 9 to 5, negative 4, 5 to 3, negative 2. So the change in the y over the change in the x will be negative 5 over 2, negative 4 over 2, and negative 2 over 2. So you can see that's negative 2 1/2, negative 2, and negative 1. So negative 2 1/2, negative 2, negative 1, because those are negative, those are actually increasing. So that must mean the second order of f double prime of x is greater than 0. So this is decreasing at an increasing rate. One more of these. Here are the y-coordinate 15, 14, 11, 2. See those y values are decreasing. So f prime of x would have to be less than 0. And if we look at the change in the x and the change in the y, x increases by 3, then by 2, then by 5. The y-coordinate decreases by 1, decreases by 3, and then decreases by 9. So if we look at the slope between these points that we're given, we have negative 1/3, negative 3/2, and negative 9/5. That's negative 1/3, that's negative 1 1/2, that's negative 1 4/5. You can see this time the slopes are actually getting more negative, in other words, they're decreasing. So that means that f double prime of x would have to be less than 0. So this is an example of a function that's decreasing at a decreasing rate. Now let's take a look at some applied problems. It says traffic flow is defined as the rate, so traffic flow is the rate itself, at which automobiles pass through an intersection measured in automobiles per minute. The traffic flow of a particular intersection is modeled by this function f. So this represents traffic flow right here. And it applies from 0 to 60. And it says, is the traffic flow increasing or decreasing at time 3? So whenever you want to know if something's increasing or decreasing, you use its derivative. This time we want to know is traffic flow itself, which f of t is, increasing or decreasing. So we need to find f time of t to see whether it's positive or negative. So this t plus 1, that's like 4t plus 1 to the 1/2. So when you take the derivative, that'd be 1/2 times 4 is 2, and then t plus 1 to the negative 1/2. Technically use the chain rule here, but the derivative inside t plus 1 is just 1. And then same thing here, the chain rule on this one. Derivative of cosine is negative sine, that cancels out the negative there to make it positive sine of pi t, times the derivative inside, derivative of pi t, pi is just a constant, so just like the derivative of 3t would be 3, the derivative of pi t is pi. And then if we simplify that in our next step, f prime of t would be 2. If we move that to the denominator to get rid of the negative exponent, put it in radical form, that'd be the square root of t plus 1. And we can bring this pi out in front, times the sine of pi t. Now, let's go ahead and substitute in time 3 to see if this is positive or negative. So f prime of 3 equal 2 over the square root of 3 plus 1 plus pi times the sine of 3 pi. So you get 2 over, that's the square root of 4, which is 2, plus pi. Sine of 3 pi is 0. That works that out, so you just get 1. So that's positive. So that means traffic flow must be increasing. So we can say, to turn this question into a statement, at t equals 3, traffic flow is increasing. And you give a reason for your answer. So your justification, same thing. You'd say since f prime of 3 is positive, you can say it's greater than 0. And in part B it says, at time 3 is the traffic flow increasing at an increasing rate, increasing at a decreasing rate, decreasing at an increasing rate, or decreasing at a decreasing rate. Well, we already know it's increasing, so based on part A, so we know it's not decreasing at a decreasing rate or decreasing at an increasing rate. So we just need to know if the rate itself is increasing or decreasing. So that would come from the second derivative. So let's find f double prime of t. So we've got our first derivative right here. So if we use this form right here, use the power of negative 1/2 times 2 is negative 1. And t plus 1 to the negative 3 out is t, and the chain rule is just multiply it by 1 the derivative inside. And then if we just leave that pi out in front, right here, just bring out the derivative of sine, okay, we'll need the chain rule, is cosine pi t, but again, the derivative inside, the derivative pi t is pi. So let's go ahead and simplify this. We'll always substitute in 3. F double prime of t is negative 1 over the square root of t plus 1 cubed. And you can bring that pi out in front with this pi to make it pi squared cosine of pi t. And now we can substitute in 3. See if this is positive or negative. So f double prime of 3 be negative 1 over the square root of 3 plus 1 cubed plus pi squared times the cosine of 3 pi. Let's see, that's negative 1 over, that's the square root of 4 is 2, cubed is 8. Cosine of 3 pi is negative 1, that's implicit pi, so that makes that negative pi squared. You can see this is negative, so that means at t equals 3, traffic flow is increasing at a decreasing rate. Now, if we hadn't already justified it in part A, I would justify it here by saying f prime of 3 is greater than 0. But here, we already justified that part A, so we can just say, use the second part since f double prime of 3 is less than 0. We already justified that it was increasing. Now we're just justifying it with a decreasing rate. Okay, let's take a look at another example. This one's a little bit different. It says for time between 0 and 30, the rate of change, in other words for the derivative, of the number of mosquitoes on malaria island at time t days is modeled by this function in mosquitoes per day. But this says in part A, is the number of mosquitoes increasing or decreasing at time 6? So, notice what it's asking for. It doesn't say is m of t. M of t is the rate. It doesn't say is the rate of number of mosquitoes increasing or decreasing at time 6. Is the number of mosquitoes increasing? And notice there's already mosquitoes per day. So this is already the derivative of the number of mosquitoes. So to see if the number of mosquitoes is increasing or decreasing, you would just plug in 6, substitute in 6. before we calculate it, let's see how that's different than the previous problem. The previous problem said, is the traffic flow increasing or decreasing? And this f of t was traffic flow, so we needed its derivative. Notice its units were automobiles per minute. So if it said is the number of automobiles increasing or decreasing, then we wouldn't need to take the derivative because this is already the derivative of the number of automobiles. It says is traffic flow increasing or decreasing, and f of t, it says traffic flow is defined by f. So it really depends on what they ask you for it, whether you need the derivative or not. In this case, it's the number of mosquitoes increasing or decreasing, and this is already the derivative of the number of mosquitoes. You can see by the units, mosquitoes per day. So if we simplify that, that'd be 36 times the sine of pi over 6, be 1/2, that'd be positive 18. So we can say at t equals 6, number of mosquitoes is increasing since, well, actually we don't have to justify this. We'll save that for next one. You could, but it doesn't ask you to, it just says it's increasing. Part B, though, says at time 6 is the number of mosquitoes increasing at an increasing rate, increasing at a decreasing rate, increasing at an increased rate, or decreasing at a decreasing rate. So we've already figured out it's increasing, so it's not decreasing at a decreasing rate or decreasing at an increasing rate at time 6. But we just need to know whether the rate is increasing or decreasing. And this is, m of t is the rate of the number of mosquitoes. So we just need its derivative, m prime of t. And you can see to take the derivative of that, we need the product for overall. So one thing I do to rewrite this, so to make it a little simpler, I'll say m of t equals t squared times the sine. Now we are going to need the chain rule because there's a function inside of sine, but if you leave it as pi over t, we'd also need to use the quotient rule inside it. So to make it a little simpler, remember pi is just a constant, so you can just write it as pi t to the negative 1. And then we still need the chain rule, but not the quotient rule anymore. And let's go ahead and use the product rule. So using the product rule, the derivative of the first one, the derivative of t squared is 2t, times the second one as it is, times the sine pi t to the negative 1, and then plus, first one as it is, t squared, times the derivative of the second one, that's where we need the chain rule. Start with the outside, the derivative of sine is cosine. And then the chain rule says we need to multiply by the derivative inside using the power rule, since pi is just a constant, would just be negative pi t to the negative 2. And now let's go ahead and simplify this before we substitute in 6. For the first term, we'll just write as 2t sine, this just becomes pi over t, plus, actually not plus, and that negative out front, minus, and then notice what simplifies here. We've got t squared, if you bring that as a number, it would be t squared, so t squared over t squared, or if you add the exponents, you have to be 0. Those reduce out. So we just have the negative pi out in front, and then cosine of pi over t. Just put the negative exponents, got rid of those to make it simpler to substitute in. So now let's go ahead and substitute 6. And prime of 6, 2 times 6 times the sine of pi over 6 minus pi times the cosine of pi over 6. So the sine of pi over 6 we already saw was 1/2. It'll be 12 times 1/2 minus pi cosine of pi over 6 would be root 3 over 2. And normally 12 times 1/2, I would just make that 6. But remember, we're trying to figure out if this is positive or negative. So if we get a common number, it's a little easier. Notice this one has a number of 2, so I'm just going to leave it as 12 over 2 minus pi root 3 over 2. So that way it's easier to compare. Well, let's see, this is positive or negative, it's going to depend on whether 12 or pi root 3 is bigger. So pi is a little more than 3, and square root of 3 is a little less than 2. So if we round out to 3 times 2, that's 6, that's way less than 12. So you can definitely see this is going to be greater than 0. So now we could say at t equals 6, the number of mosquitoes is increasing, we get from part A, at an increasing rate, we got from part B, and since, give a reason for answer, since we didn't justify part A and part B, we're going to justify both of these. So it'd be since m of 6, figured out part A is greater than 0, and m prime of 6, we figured out part B, it is also greater than 0. Let's take a look at one more that's a little bit different. It says the rate in calories per minute with which Zach burns calories while running a race is modeled by this function c of t, where t is between 0 and 20. At what time is c increasing at its greatest rate? Show the work that leads to your answer. So this one's a little bit different here. So let's translate this. We want to know when is c increasing at its greatest rate. So greatest, that's another word for the most or maximum. So we want to figure out when it's at its maximum. Rate is another word for the derivative. We want to know c increasing at its greatest rate. So c's rate. So the c's rate would be represented by c prime of t. So we're basically trying to find the maximum of c prime of t and then show the work that leads to your answer. All right, so let's go ahead and find c prime first of all. So c prime of t would be, bring down the 3, something negative 1/3 would be negative t squared, plus the 2's reduce out to 11t, and that's it, equal to root 2 to 0. So that's c prime. But we want to maximize c prime. Okay? In other words, find the absolute maximum of c prime. Whenever you want to maximize or minimize something, you need to use its derivative. So we actually need c double prime of t, which would be negative 2t plus 11. And then we find the critical numbers by setting that equal to 0. You add the 2t over, you divide by 2, you get t equals 11 over 2. So that's our critical number. And then you draw your number line. Our interval here is from 0 to 20. And then label 11 halves on there, which is in that interval. So label c double prime of t, we know it's 0 right there. And then if we test something here like 0, since it's not a critical number, I'll make c prime positive. So you can test 20, I'll make c prime negative. So what this shows us is c prime of t would be increasing and then decreasing. So you can see the maximum of c prime would have to be at 11 over 2. And so what time? So that is the time. So it would be at t equals 11 over 2. The units would be, let's see, minutes. And that concludes the notes for AP Calculus on the topic of increasing and decreasing rates in real-world applications.